Number 5 is the indefinite integral of x over 16x to the fourth minus 1 dx. So this is a rational expression. The degree of the numerator is not greater than or equal to the degree of the denominator, so I don't start with long division. What I need to do is factor this guy here and just do partial fraction decomposition. If I were to factor that denominator, well, that would factor as 4x squared plus 1 times 4x squared minus 1, because it's the difference of squares. Well, this guy here is prime, but this guy here I can continue to factor, so this in the end is going to be x over 4x squared plus 1 times, and this guy here factors as 2x minus 1 times 2x plus 1. So now I'm going to set up my partial fraction decomposition. I'm just going to bring those terms down first and then set it up. I have 3 separate denominators. I have 4x squared plus 1. Well, 4x squared plus 1 is an irreducible quadratic. Over an irreducible quadratic, I'm going to write a linear, so I will write ax plus b. 2x minus 1 is a linear. Over a linear, I write a constant. Next letter would be c. And then the next denominator, 2x plus 1, which is linear, I write a constant. My next letter would be d. Then I multiply through by the denominator. So we're going to multiply both sides by that 4x squared plus 1 times 2x minus 1 times 2x plus 1. So again, both sides by 4x squared plus 1 times 2x minus 1 times 2x plus 1. Over here on the left, everything will cancel and you're just left with x. On the right, when you distribute, you would have ax plus b times 2x plus 1 times 2x minus 1. Then you would have c times 4x squared plus 1 times 2x plus 1. And then you'd have plus d times 4x squared plus 1 times 2x minus 1. Now remember, I said that this was an irreducible quadratic. When I have irreducible quadratics, I usually like to multiply everything out, even though sometimes that does take longer, because you're going to need that system of linear equations in order to solve for your variables. So let's go ahead and take the time and multiply all this out. I'm going to take it a piece at a time. If I distribute these two together, I would end up with 4x squared minus 1. Plus c. If I distribute these two together, I would have 8x cubed plus 4x squared plus 2x plus 1. If I multiply these two together, I would have 8x cubed minus 4x squared plus 2x minus 1. Now let's distribute these two, ax plus b times 4x squared minus 1. If I distribute here, I have 4ax cubed plus 4bx squared minus ax minus b. Distributing in my c, I have 8cx cubed plus 4cx squared plus 2cx plus c. Distributing the d, I'd get 8dx cubed minus 4dx squared plus 2dx minus d. Now let's collect our terms. So let's highlight and collect all our x cubed terms. This is x cubed, this is x cubed, and this is x cubed. So this would mean that x would equal x cubed, and I'd have 4a plus 8c plus 8d. Then let's collect all our x squared terms. This is x squared, this is x squared, and this is x squared. So I'd have plus x squared and then 4b plus 4c minus 4d. Then let's collect all of our linear terms. So we have negative ax, 2cx, and 2dx. Factoring out the x, that's negative a plus 2c plus 2d. And finally, let's collect all the constants. If I'm collecting all the constants, I would have plus negative b plus c minus d. Now let's set up the system of linear equations. Well, this would be the coefficient of x cubed. I don't have an x cubed over here, so I know that 4a plus 8c plus 8d would equal 0. Well, this would be the coefficient of x squared, but I don't have an x squared over here, so I know that 4b plus 4c minus 4d would equal 0. Well, this would be the coefficient of my x term. Well, the coefficient of my x term is 1, so I know that negative a plus 2c plus 2d would equal 1. And then finally, this is my constant. Well, I don't have a constant over here, so I know that negative b plus c minus d would equal 0. So let's write this in our matrix. Remember, we have 4 unknowns. We have a, we have b, c, d, and then we're going to need a column for the answers. For my first row, a would be 4. There's no b, so I would write 0. C is 8. D is 8. The answer is 0. For my second row, I have no a. B is 4. C is 4. D is negative 4. The answer is 0. Third row, negative 1. I don't have a b, so that's 0. And then 2, 2, 1. My last row, I don't have an a, so that's 0. And then negative 1, positive 1, negative 1, 0. And this is what I'm going to put into the calculator. Remember, the calculator is going to need us to do second and then matrix. And then we scroll 1 over to edit and hit enter. I always put all my matrices in letter A. This is a 4 by 5 because I have 4 rows and 5 columns. So I hit 4, enter, and then 5, enter. Now I start putting in those numbers. 4, and then 0, 8, 8, 0. 0, 4, 4, negative 4, 0. Negative 1, 0, 2, 2, 1. And finally 0, negative 1, 1, negative 1, and then 0. Then hit second and quit, and then second and matrix again. Scroll 1 over to math, and then up to RREF for reduced row echelon form. Hit enter, and then second and matrix one last time. Hit enter for matrix A, and enter again, and there's the solution. Let's make these into fractions. Hit math, and then enter twice to get a fraction. Well, this, remember, is what A is. Well, A is going to equal negative 1/2. B is going to equal 0. C is going to equal 1/8. And D is going to equal 1/8. So I can look here and say this tells me that A was equal to negative 1/2. B was equal to 0. C is equal to 1/8. And D is equal to 1/8. Because remember, this first row was for A, and A is negative 1/2. Second row for B, B is 0. Third row for C, C is 1/8. Last row for D, D is 1/8. Now let's put this back into our integrals and then integrate. So recall, we had ax plus b over 4x squared. So my a is negative 1/2 x plus b. Well, b is 0, so I don't need to say plus 0. And that's over 4x squared plus 1 dx plus the integral of c, and c is 1/8, over 2x minus 1 dx plus the integral of d, and d is also 1/8, over 2x plus 1 dx. Let's factor out all our constant multipliers. So this is going to be negative 1/2, the integral of x over 4x squared plus 1 dx, plus 1/8, the integral of 1 over 2x minus 1 dx, plus 1/8, the integral of 1 over 2x plus 1 dx. Well, this one right here isn't linear, so we might want to use a u-sub to find the answer there, but we know that the other two are linear, so this here and this here will integrate as a 1 over u du. We just need to make sure that we multiply it by the reciprocal of the coefficient of the x term. So that's a 2, we multiply it by a half. And then the natural log of the absolute value of 2x minus 1, and then same thing here, 1/8, reciprocal of this guy, 1/2, and then the natural log of the absolute value of 2x plus 1 plus c. So let's figure out for this guy. Well, if I do a u-sub for that guy, if u is equal to 4x squared plus 1. The derivative du would equal 8x dx. I don't have an 8x dx, I divide by 8, and 1/8 du is going to equal x dx. So if I bring this guy down, this is negative 1/2 times 1/8 times the integral of, and this becomes a 1 over u du. And if I clean all the rest of this up, this is 1/16 the natural log of the absolute value of 2x minus 1 plus 1/16 the natural log of the absolute value of 2x plus 1 plus c. Here this becomes a negative 1/16, and then it's the natural log of the absolute value of u. And then finally we're going to get out of u's and go back into x's. And we end up with negative 1/16 times the natural log of the absolute value of 4x squared plus 1, and then plus 1/16 times the natural log of the absolute value of 2x minus 1, plus 1/16 times the natural log of the absolute value of 2x plus 1 plus c. Number 6 is the indefinite integral of 1 over x minus 1 squared times x plus 4 dx. Well, I need to go ahead and decompose this rational expression. So I know that 1 over x minus 1 squared times x plus 4 is going to equal, well, I have a repeated linear here. X minus 1 squared, I need to account for it to the first power and it to the second power. And then I have that x plus 4. Each one of those is linear, so over each one of those I need to write a constant, a, b, and c, because this is just considered a repeated linear. It's only a quadratic if the squared term is on the inside. Multiplying through by the denominator of x minus 1 squared times x plus 4. Same thing here, x minus 1 squared times x plus 4. I end up with 1 is equal to a times x minus 1 times x plus 4 plus b times x plus 4 plus c times x minus 1 squared. Let's do this one by convenient values. So if I'm choosing convenient values, what should I plug into here so that that will cancel? Well, x equal 1. If x is equal to 1, I end up with 1 is equal to a times 0 times 5, well that's going to cancel, plus b times 5 plus c times 0 squared, which is going to cancel. So I have 1 is equal to 5b, which means that b is equal to 1/5. Now what do I plug into this? So that term cancels, a negative 4. Therefore x will equal negative 4. Well, if x is equal to negative 4, I have 1 is equal to a times, this is going to be negative 5, and then that's 0, so that'll cancel, plus b times, and this is going to be 0, so that'll cancel, plus c times negative 5 squared. Well, negative 5 squared is 25, so I have 1 equals 25c. Therefore, I know that c equals 1 over 25. Well, I don't have any other number to choose because notice here, this would be negative 4, and here this would be 1, so I have to choose another convenient value. Just choose an easy number to work with. I like choosing 0. So let's see what happens when x is equal to 0. When x is equal to 0, this is still 1, and that's going to equal a times, well, this is going to be 0 minus 1, which is negative 1, and then 0 plus 4, which is positive 4, plus b, but I already know what b is, that's 1/5, and then times 0 plus 4, which is 4, plus c, well, I already know what c is 1/25, and then 0 minus 1, which is negative 1 squared. So I have 1 is equal to negative 4a plus 4/5 plus 1 over 25. Well, 4/5 plus 1/25 is going to equal 21 over 25. Subtracting 21/25 from both sides, and I get 4 over 25 is equal to negative 4a. Dividing both sides by negative 4, I get a is equal to negative 1 over 25. Now that I've solved for a, b, and c, let's go ahead and put it back in the integral. So I have the indefinite integral of a, which is negative 1 over 25, divided by x minus 1 dx plus the integral of b, which is 1 over 5, divided by x minus 1 squared dx. Finally, the integral of c, which is 1 over 25, divided by x plus 4 dx. Let's go ahead and factor out those constant multipliers. This becomes negative 1 over 25, the integral of 1 over x minus 1 dx, plus 1 over 5, the integral of 1 over x minus 1 squared dx, plus 1 over 25, the integral of 1 over x plus 4 dx. Well, I know that this guy right here and that this guy right here are just going to be the natural log of the absolute value, but the one in the middle here I really should use a u sub for. So if u is equal to that denominator x minus 1, the derivative du would equal dx. That's perfect, that's what I have. So we would really rewrite that integral as 1/5 the integral of 1 over u squared du. Well, that's the same as u to the negative second du. Bringing this down and bringing this down. If we integrate negative 1 over 25, the integral of 1 over x minus 1 dx, we get negative 1 over 25, the natural log of the absolute value of x minus 1. And then this is plus 1/5. When I integrate u to the negative second, that becomes u to the negative first over negative 1. And then when I integrate my other term here, that's 1 over 25, the natural log of the absolute value of x plus 4 plus c. Getting out of u's and back into x's, I end up with negative 1 over 25 times the natural log of the absolute value of x minus 1. And then this is negative 1/5. And then u to the negative first would be 1 over x minus 1 because u is x minus 1. And then plus 1 over 25, the natural log of the absolute value of x plus 4 plus c. Let's look at our last one, number 7. Number 7 is the indefinite integral of secant squared x over tangent squared x plus tangent of x dx. Well, this isn't really a rational expression because secant and tangent are not polynomials. And if we think back to what we learned in trig integrals, we said if secant is even and positive, which it is, we saved a secant squared and we became a power of the tangent. Well, if we were to do that, saving the secant squared and becoming a power of the tangent, we would let u equal the tangent of x. Well, then the derivative du would equal secant squared of x dx. So this actually becomes the indefinite integral of 1 over u squared plus u du. Well, the only difference between what we did in 8.3 and what we are doing now is that now we'd actually know that the only way to solve this is by using partial fraction decomposition, because at this point we are a rational expression. So we need to decompose this guy before we can solve this. Well, if I factor it, it has a common factor of u, I'd get u times u plus 1. Then decomposing it, I have two separate denominators, u and u plus 1. Over both of those linears, I write constants, so a and b. Then I multiply by the denominator, so I'm going to multiply both sides by that u times u plus 1. Here they're canceling, and I get 1 is equal to, and then a times u plus 1 plus b times u. Let's use convenient factors again. What's going to cancel this guy? Well, a negative 1. If u is equal to negative 1, I get 1 is equal to a times 0, which will cancel, plus b times negative 1. Therefore, I get 1 is equal to negative b, or b is equal to negative 1. What's going to cancel this guy? Well, a 0. So if u is equal to 0, I get 1 is equal to a times 0 plus 1 is 1, plus b times 0, that guy's going to cancel, and I just get a is equal to 1. Therefore, I know that I could rewrite this as the indefinite integral of a, which is 1, over u, du plus the indefinite integral of b, which is negative 1, over u plus 1 du. Factoring out this negative 1, And integrating both of these, you end up with this is the natural log of the outside value of u minus the natural log of the outside value of u plus 1 plus c. Your last and final step is to get out of u's and go back into x's. Well, we know that u is equal to the tangent of x, so we end up with the natural log of the absolute value of the tangent of x minus the natural log of the absolute value of the tangent of x plus 1 plus c. That's it for partial fractions.